In 2012, physicists found a single particle that confirmed something invisible fills all of space, the Higgs field. It was called one of the greatest discoveries in history, and yet it left a stranger question wide open, one that finding a single Higgs boson could never answer. Because the field that gives the universe its substance is predicted to do something almost no one talks about. It interacts with itself. It pushes on its own presence. And the only way to test that hidden rule is to force nature into something it almost never does, to create two Higgs bosons inside the very same collision. Not two collisions side by side, two born together in one violent instant. It is among the rarest events the Large Hadron Collider can make, and hidden inside it may lie the shape of reality's deepest foundation. But why two? Before we go any further, if questions like this are the kind of thing you love sitting with, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Think about what it actually means to discover something invisible. For decades, physicists were almost certain that all of space, every cubic centimeter of it, the room you are sitting in, the emptiness between the stars, was filled with something. Not air, not particles in the ordinary sense, a field. A kind of presence woven into the fabric of reality that touches everything and gives the universe its weight. They had the mathematics, they had the predictions. What they did not have was proof. And the way you prove a field exists is strange and beautiful. You do not photograph the field directly. You cannot. Instead, you hit it hard enough to make it ripple. And if you make it ripple, a particle appears, a tiny, fleeting bump in the field that flickers into existence and vanishes almost instantly. Find that particle, and you have found the field. That particle is the Higgs boson, and in 2012, after one of the largest scientific efforts ever assembled, two enormous detectors buried beneath the border of France and Switzerland caught it. The Higgs field was real. The presence that fills space was no longer a hypothesis. It was confirmed. And for a brief moment, it felt like the story was finished. The last missing piece of the standard model clicked into place, and the textbooks were rewritten. But here is the part that almost nobody outside of physics ever hears. Finding that single particle did not finish the story. In a sense, it barely started a much deeper one. Because confirming that the Higgs field exists is a completely different thing from understanding how that field behaves. And it turns out the most important question about the Higgs field is not whether it is there. It is how the field acts upon itself. That is the question one Higgs boson could never answer. And the only known way to even begin answering it is to do something almost absurdly difficult. To make two Higgs bosons appear inside the very same collision. Not two separate discoveries, two born together in a single violent instant. So tonight, we are going to understand exactly why. Let me start by being very precise about what a Higgs boson actually is, because this is where most explanations quietly go wrong. The Higgs boson is not a little ball. It is not a fundamental object sitting in space the way a marble sits on a table. The Higgs boson is an excitation of the Higgs field, a ripple, a disturbance, a localized vibration in something that is already everywhere. The field is the fundamental thing. The boson is just what you see when you pour enough energy into one spot to make the field jump. Imagine a perfectly still pond, stretching infinitely in every direction. The pond is the field. It is always there. Now imagine flicking the surface hard enough to send up a single splash. That splash is the boson. It rises, it exists for an instant, and then it falls back and disappears. The pond remains, the splash does not. This distinction matters enormously for everything that follows, so let me make it concrete. When the Large Hadron Collider produces a Higgs boson, it is not pulling a Higgs boson out of storage somewhere. It is not assembling one from spare parts. It is depositing a tremendous amount of energy into a tiny region of space and momentarily exciting the Higgs field so violently that a ripple, a boson, pops out. And that ripple does not last. The Higgs boson is one of the most short-lived things in all of nature. It exists for roughly a 10^60th of a second before it decays into other particles. Written out, that is a decimal point followed by 21 zeros before you reach the first real digit, measured in seconds. It is gone almost the instant it is born. You could never hold one. You could never store one. You could never line them up on a shelf. By the time the field has finished its splash, the Higgs boson is already gone, having transformed into a spray of lighter particles that fly outward into the detector. To grasp just how fleeting this is, consider what that lifetime actually rules out. A 10^60th of a second is not merely brief by human standards, it is brief by the standards of the particles themselves. In the time a Higgs boson exists, light, the fastest thing in the universe, travels a distance far smaller than a single atom. The Higgs boson is gone before it could cross the width of the nucleus at the center of an atom more than a handful of times. There is no instrument, and there could never be an instrument, fast enough or small enough to reach in and touch a Higgs boson while it lives. By the time any detector layer registers anything, the Higgs boson itself has long since ceased to exist, and only its decay products remain. This is also why a Higgs boson can never be caught in the act of existing. Most things we call short-lived still last long enough to be detected directly, to be interacted with, to be measured while they are still present. The Higgs boson grants no such opportunity. There is no probe quick enough to reach it before it decays, because the act of probing anything at all takes longer than the Higgs boson's entire existence. It is present, and then it is not, with no interval in between long enough for the outside world to register that it was ever there. That single fact already tells you something about why this whole endeavor is so hard. Whenever you hear that physicists are trying to make two Higgs bosons at once, your instinct might be to picture two little objects being manufactured side by side, like two coins coming off a press. Throw that picture away. What is really happening is far stranger and far more delicate. Two ripples in the same field, made from the same burst of energy, in the same collision, in the same fleeting instant, and both of them decaying almost immediately into showers of other particles, leaving only an indirect trace of their brief existence. So let me address the phrase head-on, because the entire subject lives or dies on this one point. What does making two Higgs bosons at once actually mean? It means producing a Higgs pair within a single proton collision. One collision, one event. Out of that one event, two Higgs bosons emerge together. This is completely different from a far more ordinary situation, and the difference is the whole game. Inside the Large Hadron Collider, protons are not fired one at a time. They are bunched into dense packets, and when two packets cross, dozens of separate proton collisions can happen almost simultaneously, scattered across the same tiny region. Now imagine that in one of those collisions a single Higgs boson is made, and then, completely independently, in a different collision happening nearby at almost the same moment, another single Higgs boson is made. You now have two Higgs bosons in your detector at roughly the same time, but that is not what we are talking about. Those are two unrelated events that each happened to produce one Higgs. They share nothing. They came from different collisions, different protons, different bursts of energy. They tell you nothing new. The thing physicists are hunting for is the genuine article. Two Higgs bosons that came from the same collision, born from the same single interaction, sharing a common origin. That is what is meant by a Higgs pair, or di-Higgs production. And the reason the distinction is so critical is that only the genuine pair, the two bosons that emerged together from one event, carries the information physicists are desperate to extract. Two accidental, unrelated Higgs bosons sitting in the detector at the same time are just a coincidence. A true pair, forged in a single collision, is a message from the deepest layer of the Standard Model. Telling those two situations apart is one of the central challenges of the entire experiment, and we will return to it. For now, hold on to the core idea. Two at once means two from one. Two ripples raised by a single strike on the field. Now, why is this so rare? Because here is the uncomfortable truth. Even making one Higgs boson is staggeringly difficult, and making two together is rarer still by a factor that almost defies belief. Let me put some scale on this. The Large Hadron Collider accelerates protons to within a hair's breadth of the speed of light and smashes them together hundreds of millions of times every second. Out of all those countless collisions, only a tiny fraction produce a Higgs boson at all. The Higgs is not something nature hands out freely. The vast majority of proton collisions produce ordinary, well-understood debris, sprays of more common particles that physicists have studied for generations. A single Higgs boson shows up only once in a great many billions of collisions. And that is the easy case. A Higgs pair is roughly 1,000 times rarer than a single Higgs. Let that number settle for a moment. If single Higgs production is already a needle in an enormous haystack, then Higgs pair production is a needle hidden inside 1,000 of those haystacks stacked together. For every 1,000 collisions that manage to make one Higgs boson, only about one will make two together. This is why, even after years of running and trillions upon trillions of collisions, physicists have only begun to glimpse the faintest possible hints of Higgs pair production. They have not confirmed it cleanly. They have not measured it precisely. They are still, in a very real sense, at the threshold, gathering just enough events to start asking whether the process is happening at the rate the theory predicts, or whether something unexpected is going on. The signal is that faint. The events are that scarce. You might reasonably ask why anyone would chase something so vanishingly rare, something so hard to produce that you can count the promising candidate events on a manageable scale even after years of effort. And the answer is that the rarity is not a bug. The rarity is the point. The reason Higgs pair production is so precious is precisely because of what has to happen for two Higgs bosons to emerge from one collision. To make a pair, the universe has to do something it does not have to do when it makes a single Higgs. It has to let the Higgs field interact with itself. And that self-interaction, that tendency of the field to push and pull on its own presence, is one of the last great untested predictions of the Standard Model. We will spend a great deal of time on exactly what self-interaction means, because it is subtle, and because it is easy to describe it badly. But for now, simply understand the stakes. Hidden inside the rate at which Higgs pairs appear is a clue about how the Higgs field behaves toward itself, and that behavior may be the closest thing we have to a fingerprint of the field's true nature. Let me slow down and make sure the foundation is solid, because the leap from one Higgs to two Higgs is not a small step. It is a step into genuinely new territory. When the Large Hadron Collider made single Higgs bosons in 2012 and in the years that followed, it confirmed that the field exists and let physicists measure some of its basic properties. Its mass, for example, which came out to about 125 giga-electron volts, a specific and now well-measured value. They confirmed how the Higgs field couples to other particles, how strongly it grabs onto the particles that pass through it. All of this was extraordinary, and all of it built confidence that the Standard Model was correct. But notice what every single one of those measurements had in common. They all involved the Higgs field interacting with something else. The Higgs and a pair of photons. The Higgs and a pair of heavier particles. The Higgs and the particles it decays into. In every case, the field was reaching out and touching something other than itself. What none of those measurements could test is whether the Higgs field reaches out and touches itself. And that is not a minor footnote. The way the Higgs field interacts with itself is built directly into the mathematical heart of the theory. It is encoded in the very equation that describes the field's behavior. The standard model does not merely predict that the field exists, it predicts a specific shape to the field's behavior, a specific rule for how the field responds to its own strength. And that rule has barely been tested at all. We confirmed the field is there. We have hardly begun to confirm that the field obeys the self-interacting rule the theory assigns to it. Producing a single Higgs simply does not require the field to interact with itself. So a single Higgs can never reveal whether that self-interaction is real or whether it has the strength the standard model claims. For that, you need the field to ripple in a way that involves its own presence. You need two bosons born together. You need a pair. This is the elegant, almost poetic logic at the center of the whole effort. One Higgs boson proves the field is there. Two Higgs bosons, born from a single collision, may prove how that field acts upon itself. And there is no shortcut around it. You cannot infer the self-interaction from the easy measurements. You cannot back it out of single Higgs data. The information lives in the pair, and only in the pair, which means you have no choice but to chase the rarest of rare events and learn to read the faint signature it leaves behind. I want to be careful here not to overstate what is being claimed, because this is a place where popular explanations tend to overreach. It would be tempting to say that the Higgs boson somehow gives mass to itself as a neat little slogan. That is not what is happening, and that is not what physicists are testing. The story of how the Higgs field gives other particles their mass is a different and largely settled chapter, and we are not going to relitigate it tonight. What we are after is something distinct. The question of how the field behaves around its own resting state, how strongly the field's own presence influences its own dynamics. That is the self-interaction. And while it is intimately connected to the deep structure of the theory, it is not captured by any catchy phrase about the Higgs giving mass to itself. The reality is more subtle, more geometric, and far more interesting, and we will build up to it carefully rather than reaching for a slogan that collapses the moment you examine it. Let me also confront a misconception that the phrase "making two Higgs bosons" tends to plant in people's minds. There is an unfortunate image that creeps in, the image of CERN as a kind of factory, assembling Higgs bosons the way a workshop assembles machines, building them up piece by piece and setting them aside. Nothing could be further from the truth. CERN is not assembling anything. There is no construction, no accumulation, no shelf of finished Higgs bosons waiting to be studied. What actually happens is closer to lightning than to manufacturing. An almost unimaginable concentration of energy is forced into a microscopic point of space for the briefest possible instant. The Higgs field convulses, and out of that convulsion, two ripples leap up together. And then, in less time than it takes for light to cross the width of an atom many times over, both of them are gone, decayed into other particles. Each Higgs boson is a flicker, not a thing. The pair exists only in the moment of its own creation. Physicists never see the two Higgs bosons themselves. They only ever see the wreckage left behind after the pair has already vanished. The whole science is the science of reading footprints in the snow long after the animal has run off. And this brings us to a question that is going to shape everything that comes later. If the Higgs bosons themselves vanish almost instantly, how do you even know a pair was ever made? How do you study something that is gone before any instrument could possibly register it directly? The answer is that you do not study the Higgs bosons, you study what they turn into. When a Higgs boson decays, it does not simply disappear into nothing. It transforms into a specific set of other particles, and those particles fly outward through the layers of the detector, leaving tracks, depositing energy, triggering sensors. From that spray of debris, physicists work backward, reconstructing what must have existed a fraction of an instant earlier. It is a kind of forensic reconstruction performed millions of times per second, sifting through oceans of data for the rare pattern that says two Higgs bosons were here, born together and then gone. This is why Higgs pair production sits at the absolute frontier of what the Large Hadron Collider can do. Think about everything that has to line up. The collision has to be energetic enough and lucky enough to make a pair at all, which happens perhaps once in 1,000 times that even a single Higgs is made, which itself happens only once in many billions of collisions. A single Higgs boson is rare because the Higgs field does not couple strongly to the ordinary constituents that actually meet when two protons collide. The lightest, most common building blocks inside a proton barely feel the Higgs field at all, so they are poor at exciting it. To make a Higgs boson, the collision has to proceed through a more roundabout chain, leaning on the heaviest particles nature provides, because those are the ones the Higgs field grips most firmly. This indirectness is part of why a single Higgs surfaces only once in many billions of collisions rather than routinely. And now, stack a second requirement on top of the first. To make a pair, you do not merely need one of these already rare excitations of the field. You need the collision to be energetic enough to raise twice the disturbance, and you need the field to do something even less likely than producing a lone ripple. Each additional demand multiplies the scarcity. It is not that producing two Higgs bosons is twice as hard as producing one. It is that the conditions for a pair are so much more stringent that the rate collapses by roughly a further factor of 1,000. Rarity in this domain does not add, it compounds. And the compounding is what pushes Higgs pair production from merely difficult to very nearly at the edge of what the current collider can reach at all. Then both Higgs bosons have to decay, and the particular ways they decay determine whether the event is something you can even hope to identify amid the chaos. And surrounding every one of these precious events is a deafening roar of ordinary collisions producing ordinary particles, many of which can accidentally mimic the very signature you are looking for. Finding a genuine Higgs pair is not like spotting a bright star in a dark sky. It is like trying to hear two specific notes played once, very softly, in the middle of a stadium full of noise, and then proving that those two notes came from the same instrument, at the same moment, rather than from two separate musicians who happened to play at the same time. So step back for a moment and take in the shape of what we are dealing with. The Higgs field fills all of space. The Higgs boson is a fleeting ripple in that field, gone almost as soon as it appears. Making one of those ripples is already a monumental achievement that took the largest machine humanity has ever built. And now physicists are reaching for something 1,000 times harder still. Two ripples raised together by a single strike, because only that double ripple involves the field touching itself, and only by watching the field touch itself can we test a prediction that has sat in the theory for decades, almost entirely unverified. There is something humbling in this. We tend to imagine that once the Higgs boson was discovered, the great mystery was solved and physics moved on. But the discovery was, in a way, only the confirmation that the door exists. Walking through it, actually understanding the field on the other side, learning its internal rules, watching how it responds to its own presence, is a separate and far harder journey. And the entrance to that journey is the Higgs pair. It is the only known way to probe the self-interaction directly. It is the reason a community of thousands of physicists is willing to sift through quadrillions of collisions in pursuit of a few dozen ghostly candidate events. Because each of those events, faint and rare as it is, carries a whisper of how the foundation of reality behaves when nothing else is involved but the field and itself. I want to leave you, before we go deeper, with the precise nature of the puzzle we are about to unravel. We have established what a Higgs boson is, a ripple in an ever-present field, not a durable object. We have established what making two at once truly means. A genuine pair born from a single collision, sharply distinct from two unrelated collisions that each make one. We have established why it is so extraordinarily rare, roughly 1,000 times rarer than a single Higgs, itself a once-in-billions event, and why that rarity is exactly what makes it valuable. Because producing a pair forces the Higgs field to do something a single Higgs never requires. And we have established that the bosons themselves are never seen, only reconstructed from the debris they leave as they decay almost instantly, which makes the whole enterprise a feat of forensic reconstruction against an overwhelming background of noise. What we have not yet done is open up the heart of the matter, the self-interaction itself. What does it really mean for a field to interact with itself? Why is that self-interaction tied to the shape of something physicists call the Higgs potential? And why does that shape, that hidden geometry, matter so much that an entire generation of experiments is being organized around measuring it? Because the rate at which Higgs pairs appear is not just a number. It is a window onto the form of the field's own behavior, the curve that describes how the field settles into the state we all live inside right now. And that curve, it turns out, may hold answers to questions that stretch far beyond particle physics. Questions about why the universe is the way it is at all. For now, hold this single image in your mind, the image everything else will be built upon. Somewhere beneath the Alps, in a ring of superconducting magnets colder than deep space, protons are crashing together at nearly the speed of light. And, once in a vast while, the field that fills all of existence shudders hard enough to raise not one ripple, but two. Two Higgs bosons, born together, gone together, leaving behind only a faint and scattered trace. That trace is what we are learning to read, and what it may tell us is not whether the foundation of reality exists, but how that foundation behaves when it is left alone with nothing but itself. That is the difference between proving the field is there and understanding what the field truly is. To understand why two Higgs bosons matter so much, we have to confront an idea that sounds almost paradoxical at first. The idea that a field can interact with itself. Most of the time, when we talk about interactions in physics, we are talking about two different things affecting each other. A magnet pulls on a nail. The sun's gravity tugs on the Earth. An electron feels the push of another electron. In every familiar case, there are two distinct participants, and the interaction is the relationship between them. So what could it possibly mean for something to interact with itself? How does a single field reach out and touch its own presence? This is the conceptual heart of everything, and if we get it right, the entire purpose of producing Higgs pairs will suddenly make sense. So let me build it up slowly, from the ground, with no slogans and no shortcuts. Start again with the image of the field as something that fills all of space. The Higgs field is not empty space, and it is not a substance floating in space. It is a property that space itself possesses everywhere, a value attached to every point in the universe. And here is the feature that makes the Higgs field unlike almost anything else we know. In the universe we actually live in, the Higgs field does not rest at zero. It sits at a particular non-zero value, the same value everywhere, a kind of permanent background level that never switches off. This is deeply strange when you first sit with it. Most fields, left alone, settle down to nothing. Turn off all the sources, remove all the disturbances, and they relax to zero. The Higgs field does not. Even in the emptiest vacuum you can imagine, with every particle stripped away, the Higgs field still holds a steady, non-zero value. That resting value, the level the field naturally settles into when nothing is disturbing it, is what physicists call the vacuum state of the field. It is the floor the universe sits on. Now, why does the field settle at that particular value and not some other? Why not zero? Why not twice as much? The answer is the single most important concept in this entire story, and it is called the Higgs potential. The potential is, in essence, a rule that assigns an energy cost to every possible value the field could take. Think of it as a landscape, a curve, a shape, where the horizontal direction represents how strong the field is, and the vertical direction represents how much energy the universe pays for the field to have that strength. And just as a ball rolling around in a landscape will come to rest at the lowest point it can find, the Higgs field settles into whatever value sits at the bottom of its potential. The shape of that landscape determines everything about where the field comes to rest and how it behaves when nudged. For ordinary fields that relax to zero, you can picture the potential as a simple bowl with its lowest point right at the center, right at zero field strength. Drop a ball into a bowl like that, and it rolls straight to the middle and stays there. But the Higgs potential is not a simple bowl centered at zero. Its shape is more interesting, and that shape is the reason the universe looks the way it does. The most common way physicists describe the predicted shape of the Higgs potential is to picture something like the bottom of a wine bottle or the base of a sombrero, a surface with a little bump pushing up in the very center and a circular valley, a trough, surrounding that central bump. Here is the crucial consequence of that shape. The center, the point of zero field strength, is not the lowest point anymore. It is a small hill. The lowest points, the places where a ball would actually come to rest, lie down in the surrounding trough, away from the center at a non-zero value. So the field, seeking the lowest energy it can find, rolls off the central bump and settles down into the trough at a non-zero strength. That is why the Higgs field rests at a non-zero value throughout the universe. Not by accident, but because the shape of its potential makes the non-zero state the comfortable one and the zero state the unstable one. Hold on to that picture of the field resting in the trough, because now we can finally say what self-interaction actually means. Self-interaction is what happens because the potential is curved. If the potential were perfectly flat, the field would feel no preference, no pull toward any particular value, and disturbing it would do nothing special. But the potential is not flat. It has a definite shape, a definite curvature, walls that rise up on either side of the resting point. And the steepness of those walls, the way the landscape bends around the place where the field sits, encodes how the field responds to being disturbed. When you push the field away from its resting value, the curvature of the potential pushes back. The field's own strength feeds back into the energy it costs to change that strength. That feedback, that response of the field to changes in itself dictated by the shape of its own potential, is precisely what we mean by the Higgs field interacting with itself. It is not the field touching some other field. It is the field's value influencing how the field itself behaves, through the curve it is sitting in. Let me make this even more concrete with the rolling ball picture, because it captures the essential point. Imagine the field as a ball resting at the bottom of the trough. Now imagine giving it a small kick so that it sloshes a little, oscillating back and forth around its resting point. Those small oscillations of the field around its vacuum value, those are the Higgs bosons. A Higgs boson is, quite literally, a little quivering of the field about the bottom of its potential. And the way that quivering behaves, how it oscillates, how it might split or combine, depends entirely on the precise shape of the trough the ball is sitting in. A gently curved trough and a sharply curved trough produce different behavior. The walls of the potential, their steepness, the way they bend, all of this governs how the ripples in the field interact when there is more than one of them, and how a disturbance in the field might give rise to additional disturbances. The shape of the potential is not some abstract decoration. It is the rulebook for how the field treats its own ripples. This is where the connection to producing two Higgs bosons finally crystallizes. If the field's self-interaction is encoded in the curvature of its potential, then to test the self-interaction, you need a physical process that actually depends on that curvature. A process where the field's own ripples affect each other. And the cleanest such process is one in which the field, when excited, produces not one ripple, but two, with the production of the second ripple depending on the shape of the potential. When a disturbance in the Higgs field can transform into two Higgs bosons, the rate at which that happens is sensitive to how strongly the field interacts with itself, which is to say, to the curvature of the potential near its resting point. So measuring how often two Higgs bosons emerge together becomes a way of measuring the shape of the landscape that the entire universe is sitting in. The pair production rate is a probe of the potential's geometry. That is the thread connecting the rare double ripple in a Swiss tunnel to the deepest structure of the field that fills all of space. There is a specific number that captures this self-interaction strength, and physicists call it the Higgs self-coupling. You can think of the self-coupling as a single dial that sets how strongly the field's ripples push on one another, how steeply the potential curves in the region that matters, how readily one disturbance in the field begets a second. The standard model does not leave this dial free to be anything at all. Given everything else we have already measured, the mass of the Higgs boson, the resting value of the field, the theory makes a specific prediction for what the self-coupling should be. It hands us a number. And that prediction is one of the boldest and least tested claims in all of fundamental physics. We have measured the Higgs mass with great precision. We have measured the resting value of the field. But the self-coupling, the dial that governs the field's relationship with itself, has barely been pinned down at all. We have only the faintest experimental grip on it. The theory says it should have a particular value. Nature has not yet confirmed that it does. I want to dwell on why this gap exists, because it explains the entire urgency of the Higgs program. Every measurement physicists have made of the Higgs field up to now involves the field reaching out to something other than itself, coupling to other particles, decaying into other particles, being produced through its interaction with other particles. Those measurements are abundant and increasingly precise, and they have confirmed the standard model in detail. But not one of them tests the self-coupling, because none of them requires the field to interact with itself. The self-coupling lives in a corner of the theory that the easy measurements simply cannot reach. It is shielded from view, accessible only through processes where the field's own ripples come into play. And the most direct such process is the production of a Higgs pair. So the self-coupling sits there in the equations, a confident prediction with almost no experimental verification behind it, waiting for the one kind of measurement that can finally test it. This is not a small loose end. It is a foundational pillar of the theory that has been asserted but never properly checked. Now, I have to be very careful here, because there is a tempting way to summarize all of this that is wrong, and I want to make sure we never fall into it. It is tempting to say that the Higgs boson gives mass to itself, as though the self-interaction were just the mass generation story turned inward. That is not what the self-coupling is, and conflating the two muddies everything. The way the Higgs field endows other particles with mass is a separate mechanism, one that has been confirmed and that we are deliberately not rehashing tonight. The self-coupling is something else entirely. It is about the shape of the potential, the curvature of the landscape around the field's resting point, and how that shape governs the field's response to its own presence. It is geometry, not a recycled mass story. When you measure the self-coupling, you are not measuring how the Higgs gives itself mass. You are measuring how steeply the potential curves, how the field behaves when disturbed about its vacuum, how readily its ripples beget more ripples. Keep the focus there, on the form of the landscape, and the concept stays clean. Reach for the slogan about the Higgs giving mass to itself, and it dissolves into confusion. So we will hold the line and speak only of the potential's shape and the self-interaction it encodes. Let me push the landscape picture a little further, because the shape of the potential is even richer than a single trough suggests, and that richness is exactly what makes the self-coupling so consequential. The potential, remember, assigns an energy cost to every value the field could take. Near the resting point, where the field actually sits, the potential curves upward on both sides, forming the walls of the trough. The steepness of those walls right at the bottom is closely tied to the mass of the Higgs boson. A steeper curve near the bottom corresponds to a heavier ripple. But the potential does not stop at the immediate neighborhood of the resting point. It continues outward and upward, and the way it rises farther from the bottom, the way the curve bends as you move well away from the vacuum, is governed by the self-coupling. So the self-coupling tells you something the Higgs mass alone cannot. It tells you about the shape of the potential beyond the immediate resting point, about the broader form of the landscape, not just the narrow dip where the field currently sits. Measuring the mass tells you how tightly the field is held right at its resting place. Measuring the self-coupling tells you about the larger architecture of the valley the universe lives in. It is worth dwelling on why the theory can fix the self-coupling at all, because this is what turns the measurement into such a sharp test. The shape of the Higgs potential in the Standard Model's minimal version is described by a simple mathematical form, a curve determined by just a couple of quantities. One of those quantities sets where the bottom of the trough sits, which is to say, the resting value of the field. The other sets how steeply the curve bends. Now here is the key. Both of these are connected to things we have already measured. The resting value of the field is known, and the steepness of the curve right at the bottom of the trough is tied directly to the mass of the Higgs boson, which we measured precisely after the discovery. Once those two pieces are locked down, the form of the potential is fully determined. There is no remaining freedom. The self-coupling, the number describing the curvature away from the resting point, is no longer an independent quantity you are free to choose. It is forced to a particular value by the others. The theory, in effect, says, given what you already know about the mass and the resting value, the self-interaction must be exactly this strong, no more and no less. This is what makes the measurement so powerful, and it is worth sitting with the logic. In many areas of physics, a prediction has wiggle room. If a measurement comes out a little off, you can adjust some free parameter and accommodate it. But the self-coupling has no such escape. The Standard Model commits to a definite value with no room to maneuver. So if we measure it and it agrees, that agreement is meaningful precisely because the theory could not have wriggled out of a disagreement. And if it disagrees, that cannot be explained away by tuning some hidden knob, because there is no knob left to tune. The self-coupling is pinned by the theory's internal consistency, which means the measurement is a genuine, unhedged confrontation between prediction and reality. Few quantities in physics offer that kind of clean, all-or-nothing test, and that is a large part of why this particular number is so coveted. There is a subtlety here that deepens the point. The mass of the Higgs boson and the self-coupling both describe the same potential, but they describe different parts of it. The mass reflects how sharply the potential curves in the immediate vicinity of the resting point, the tightness of the dip the field sits in. The self-coupling reflects how the potential continues to bend as you move outward, well away from the resting point, into territory the field does not currently occupy. Think of it as the difference between measuring the steepness of the ground right beneath your feet and measuring the slope of the hillside some distance away. You could know the first with great precision and still know almost nothing about the second. That is exactly our situation. We have measured the ground beneath the field's feet, the mass, with confidence. The slope of the surrounding hillside, the self-coupling, remains almost entirely unmeasured. And in the standard model, those two are required to fit together into one smooth, predetermined landscape. Checking whether they actually do is the entire game. If the hillside does not slope the way the ground beneath our feet says it should, the simple potential we have assumed is wrong, and the landscape has a more complicated shape than the minimal theory allows. This is why physicists describe the self-coupling measurement as probing the shape of the Higgs potential in a way nothing else can. We currently know, in effect, that there is a trough and that the field rests at its bottom. We know roughly how steep the walls are right at the bottom because we know the Higgs mass. What we do not yet know, with any real confidence, is whether the broader shape of the potential matches what the standard model predicts. Does the landscape rise the way the theory says it should as you move away from the resting point? Is the curvature out there exactly what the equations demand, or is it subtly different? The standard model gives a precise answer, but that answer has not been tested, and the only way to test it is to measure the self-coupling, and the only way to measure the self-coupling is to produce and study Higgs pairs. The pair production rate depends on the self-coupling, which depends on the curvature of the potential away from its base, which is to say, on the very part of the landscape we have never been able to see. It is worth pausing to appreciate how unusual this situation is. In most of physics, the things we cannot directly see, we can at least infer from many converging measurements. But the broader shape of the Higgs potential is shielded behind a single, brutally rare process. There is no abundant phenomenon that reveals it. There is no easy backdoor. The information is locked inside the rate at which the field raises two ripples at once, and that rate is so small that we are only now, after years of running the most powerful collider ever built, beginning to gather enough events to start to constrain it. The shape of the foundation of reality is hidden behind one of the rarest doors nature offers, and prying that door open even a crack requires a heroic experimental effort. This is the strange position fundamental physics finds itself in. We are confident the field exists. We have a detailed prediction for the shape of its potential, and yet the part of that shape that matters most for the field's self-behavior is almost entirely unverified, accessible only through the faintest of signals. Let me also explain why the self-coupling sits at the edge of the standard model in a more structural sense, because this is what makes it such a sharp test. The standard model is an extraordinarily tight theory. Its pieces are interlocked. Once you fix a handful of numbers, almost everything else is determined. The prediction for the self-coupling is one of those determined quantities. Given the Higgs mass and the field's resting value, the self-coupling is fixed by the theory's internal logic. This is what makes it such a powerful test. If we measure the self-coupling and it matches the predicted value, that is a striking confirmation that the standard model's picture of the potential is correct all the way down to its self-interacting core. But if we measure it and find it does not match, if the field interacts with itself more strongly or more weakly than predicted, or in some altered way, then we will have found a crack in one of the most successful theories ever constructed. We will know that the shape of the potential is not what the standard model says, and that something beyond our current understanding is shaping the landscape. Either outcome is profound. A confirmation would validate the theory's deepest layer. A deviation would open a door to new physics. And the only way to learn which it is to measure the self-coupling through Higgs pairs. I want to gently guard against another overstatement, because it is easy to get carried away here. Measuring the self-coupling does not, by itself, hand us the complete shape of the potential in every detail, mapped out point by point. What it does is give us a powerful constraint on the curvature of the potential away from its resting point, a window onto a part of the landscape we have never glimpsed. It is a measurement of how the field interacts with itself at a particular strength, encoded in how often pairs are produced. That is enormously valuable, but it is one critical handle on the potential's shape, not a full reconstruction of the entire landscape from end to end. We should be precise about what the measurement delivers: a test of whether the self-interaction matches the standard model's prediction, and a probe of the curvature beyond the base of the trough, without inflating it into something it is not. The honest claim is striking enough on its own. We are testing, for the first time, whether the field obeys the self-interacting rule the theory assigns to it. So let us draw the threads of this together before we move on, because the logic is now complete and it is beautiful. The Higgs field fills all of space and rests at a non-zero value. It rests there because the shape of its potential, the energy landscape assigning a cost to every field value, has its lowest point not at zero, but in a surrounding trough. The field, like a ball seeking the lowest ground, settles into that trough. Small oscillations of the field about the bottom of the trough are Higgs bosons, fleeting ripples in the field. How those ripples behave, and in particular how readily one disturbance can give rise to two, depends on the curvature of the potential, on how the landscape bends around and beyond the resting point. That curvature is the field's self-interaction, captured by a single number, the self-coupling, which the standard model predicts but which has scarcely been tested. And the way to test it is to measure how often the field raises two ripples at once, because the rate of Higgs pair production is sensitive to the self-coupling, and therefore to the shape of the potential in the region we have never been able to see. That is the whole logical chain, from the field that fills space to the rare double ripple in the collider. It begins with a landscape and ends with a measurement, and every link is necessary. You cannot get to the self-coupling without the potential. You cannot get to the potential's broader shape without a process that depends on its curvature. You cannot get a process that depends on its curvature without producing two Higgs bosons together. And you cannot produce two Higgs bosons together without the largest machine humanity has ever built, running for years, sifting through an ocean of collisions for the rarest of events. The improbability of the experiment is a direct reflection of how deeply the self-interaction is hidden inside the structure of reality. But there is a complication I have been holding back, and it is essential, because without it, you would walk away with a picture that is too simple and too clean. I have been speaking as though producing two Higgs bosons is a single, direct window onto the self-coupling, as though every Higgs pair is a clean readout of the curvature of the potential. It is not that simple. Nature, as usual, makes things more tangled and more interesting than the tidy version suggests. There is not just one way for the field to produce a pair of Higgs bosons. There are several distinct quantum routes by which two Higgs bosons can emerge from a single collision, and only some of those routes actually involve the self-coupling at all. The others produce a pair without ever touching the curvature of the potential. And here is the truly subtle part. These different routes do not simply add up side by side. They overlap. They interfere with one another in the strange way that only quantum processes can, sometimes reinforcing and sometimes cancelling. The number we actually measure, the rate at which pairs appear, is the combined result of all these interfering routes tangled together. Which means that extracting the self-coupling from that rate is not a matter of reading a dial directly. It is a matter of disentangling competing quantum pathways, of comparing rates and patterns, of careful inference rather than simple observation. That tangle, the multiple routes to a Higgs pair, the interference between them, and the painstaking experimental work required to pull the self-coupling out of the mixture, is where we turn next. Because it is one thing to say that Higgs pair production is sensitive to the field's self-interaction. It is another thing entirely to actually measure that self-interaction amid the interference of competing processes and the deafening background of an environment where countless ordinary collisions can imitate the very signal you are chasing. The principle is clean. The practice is a gauntlet. And understanding that gauntlet is the key to understanding why this measurement is so hard, why it demands such staggering amounts of data, and why a confident answer about the shape of the potential that the entire universe rests upon may still be years away from our grasp. Here is the complication that turns a clean idea into one of the hardest measurements in all of science. When I described Higgs pair production as a window onto the self-coupling, I was telling you something true but incomplete. The incompleteness is this. There is no single, tidy mechanism by which the Higgs field raises two ripples at once. Nature offers several distinct quantum routes to the same destination, and they are not all the same. Some of these routes pass directly through the self-interaction, carrying within them the information about the curvature of the potential that we are so desperate to read. Others arrive at a pair of Higgs bosons without ever touching the self-coupling at all. They produce the same final outcome, two Higgs bosons emerging from one collision, but they take a completely different path to get there, a path that has nothing to say about how the field interacts with itself. And the deepest difficulty, the one that makes this measurement a genuine gauntlet, is that these different routes do not politely take turns. They happen together, overlaid on one another, and in the strange logic of quantum mechanics, they interfere. Let me build this up carefully, because the idea of interference between production routes is where many people lose the thread, and it is absolutely central to why two Higgs bosons are so hard to interpret. Consider the dominant way that Higgs pairs are made at the Large Hadron Collider. When two protons collide at enormous energy, what actually meets in the violent heart of the collision are the constituents inside them. Out of that collision, through a chain of quantum events, two Higgs bosons can emerge. But there is more than one chain that leads there. Picture two of these chains side by side. In the first, the energy of the collision excites the Higgs field in such a way that a single Higgs boson is momentarily called into being, a fleeting, virtual disturbance. And that single disturbance then splits, through the self-interaction, into two real Higgs bosons. This is the route we care about most, because the splitting of one into two is governed directly by the curvature of the potential. This route carries the self-coupling within it. If the field interacts with itself strongly, this route is enhanced. If weakly, it is suppressed. The fingerprint of the self-interaction is stamped right onto it. Now picture the second chain. In this one, two Higgs bosons emerge from the collision without ever passing through a single intermediate Higgs that splits in two. Instead, the two Higgs bosons are produced more directly, radiated out through a different arrangement of the quantum process, attached to the heavy particles that mediate the collision, rather than budding from a self-interaction. This route also produces a genuine Higgs pair from a single collision, but it never involves the field interacting with itself. The self-coupling plays no part in it. If you could somehow isolate this route and study it alone, it would tell you nothing about the shape of the potential. It is a way of making two Higgs bosons that sidesteps the very thing we are trying to measure. So already you can see the problem taking shape. We want the self-coupling, which lives in the first route. But nature insists on also producing pairs through the second route, which is blind to the self-coupling. If these two routes simply added together, if the total rate were just the first route's contribution plus the second route's contribution, side by side and independent, the situation would be manageable. We could, in principle, account for the second route and subtract it away. But that is not how quantum mechanics works. In the quantum world, when two routes lead to the same final outcome, and you cannot tell which route nature actually took, you do not add the rates of the two routes. You combine the routes themselves before computing the rate, and when you do, they interfere. They overlap like two waves meeting on the surface of a pond. And like waves, they can reinforce each other where they are in step, or cancel each other where they are out of step. This is the crucial and almost maddening fact about Higgs pair production. The two main routes interfere destructively. They work against each other. Where one route would push the production rate up, the other tends to pull it down, and the result is a partial cancellation. The pair production rate we actually observe is not the sum of two contributions, but the result of two contributions fighting each other to a near standstill. This is a large part of why Higgs pairs are so staggeringly rare in the first place. It is not only that each route is individually small, it is that the routes partially cancel, suppressing the combined rate even further. Nature is, in effect, hiding the signal twice over, once by making each pathway rare, and again by arranging for those pathways to interfere destructively and shrink the total still more. The very process that carries the information we want is muted by its own internal structure. And here is the consequence that reshapes the entire experimental strategy. Because the routes interfere, the rate of Higgs pair production does not depend on the self-coupling in a simple, straight-line way. If you imagine turning the self-coupling dial, making the field's self-interaction stronger or weaker than the standard model predicts, the observed pair production rate does not just rise or fall proportionally. It responds in a more complicated fashion, because changing the self-coupling changes the first route, which changes how it interferes with the second route, which changes the degree of cancellation. The relationship between the self-coupling and the measured rate is curved and subtle. There can even be a value of the self-coupling at which the cancellation is least effective and the rate is largest, and other values where the cancellation deepens and the rate shrinks toward a minimum. So the measured rate alone does not point to a single answer. The same rate might be consistent with more than one possible value of the self-coupling. It is worth understanding this relationship more concretely because it is one of the most counterintuitive features of the measurement and shapes how the data must be interpreted. Picture the self-coupling as a dial you can turn and imagine watching the predicted pair production rate as you turn it. You might expect that as you crank the self-coupling up, the rate simply climbs, and as you crank it down, the rate simply falls. But that is not what happens, and the reason is the destructive interference we just discussed. At the standard model's predicted value, the two main routes partially cancel, holding the rate down to a small number. Now suppose you turn the dial away from that value. As you do, you change the strength of the route that carries the self-coupling, which changes how completely it cancels against the route that does not. At some settings, you make the cancellation worse, driving the rate down toward a minimum. Push the dial further in the same direction, and the cancellation begins to fail. The roots stop fighting each other so effectively, and the rate climbs back up. The result is that the rate does not respond to the self-coupling in a straight line. It dips to a low point at one particular value and rises on either side of it, like a valley rather than a ramp. This valley-shaped relationship has a sharp and frustrating consequence. Because the rate falls and then rises, a single measured rate can correspond to two different values of the self-coupling, one on each side of the valley. If you measure a certain number of pairs, you cannot tell from that number alone which side of the valley nature actually sits on. The Bayer count leaves a genuine ambiguity, two distinct possible answers consistent with the same observation. This is precisely why the total rate, on its own, is not enough, and why physicists must also study the detailed shape of the events. The two candidate values of the self-coupling, though they produce the same overall number of pairs, do not produce pairs with identical characteristics. They distribute the energy and the angles of the two Higgs bosons differently. So, by examining not just how many pairs there are, but how they are arranged, physicists can often break the tie, ruling out one of the two candidate values and pointing to the other. The ambiguity that the rate alone cannot resolve is resolved by the pattern. This is the deepest reason the measurement demands both quantity and shape together. The interference makes the rate ambiguous, and only the distribution can disambiguate it. This is why physicists cannot simply count Higgs pairs and read off the self-interaction strength. The counting is only the beginning. Interpreting the count requires untangling the interference, modeling each root, and accounting for how they combine. This brings us to a point I have to state plainly, because it corrects a misconception that the whole framing of the subject tends to encourage. It is tempting to imagine that each detected Higgs pair is a little isolated measurement of the self-coupling, that you find a pair, and inside it sits a clean number telling you how the field interacts with itself. That is not how it works, and believing it would lead you badly astray. No single Higgs pair event carries the self-coupling on its face. Any individual pair could have come from the self-coupling root or from the root that ignores the self-coupling entirely, and you cannot tell which by looking at one event. The self-coupling reveals itself only statistically, in the aggregate, in the overall rate at which pairs are produced across enormous numbers of collisions, and in the detailed distributions of the properties of those pairs. You have to gather many candidate events, measure not just how many there are, but how they are arranged, how the two Higgs bosons share energy, how they are angled relative to each other, how their combined properties are distributed, and compare that whole picture against what each combination of roots would predict for different values of the self-coupling. The self-coupling is a conclusion drawn from the pattern of many events, never a reading taken from any one of them. Let me make this concrete, because the distinction between the total rate and the detailed pattern is itself a powerful tool. The two roots, the one that carries the self-coupling and the one that does not, do not produce Higgs pairs with identical characteristics. They tend to produce pairs with somewhat different distributions of energy and momentum. The root that runs through a single virtual Higgs splitting in two, for instance, tends to populate certain configurations of the pair differently than the root that radiates the two bosons more directly. So even though any single event is ambiguous, the collection of events carries information in its shape. If the self-coupling were larger or smaller than the standard model predicts, it would not only shift the total number of pairs, it would subtly reshape the distribution of their properties, pushing more events into certain configurations and fewer into others. By studying both the overall rate and the detailed shape of the distributions together, physicists can break some of the ambiguity that the rate alone leaves open. The pattern helps distinguish between values of the self-coupling that the Bayer count cannot separate. This is why the measurement is described as comparing the total rate and the detailed properties of many candidate events. It is not one measurement, but a joint reading of quantity and shape, each constraining the answer in a different way. Now layer on top of all this the brutal reality of where these events are happening, because the interference of quantum roots is only half the battle. The other half is the environment, the deafening, chaotic, overwhelming environment of a proton collision. I want you to appreciate just how hostile this environment is to a delicate measurement. Protons are not simple, clean objects. They are seething bundles of constituents. And when two protons collide at the energies the Large Hadron Collider reaches, the result is not a tidy little interaction, but an explosion of activity. Vast numbers of ordinary particles spray out in every direction from processes that have nothing whatsoever to do with the Higgs field. These ordinary processes are millions, billions of times more common than Higgs pair production. They form a roaring background, a constant torrent of mundane events, and buried somewhere in that torrent, once in a great while, is the rare double ripple we are hunting for. But the background is not just loud, it is treacherous, because some of those ordinary processes can imitate the signature of a Higgs pair. To understand why, we have to remember what happens to the Higgs bosons after they are made. As we established, a Higgs boson does not survive. It decays almost immediately into other particles, and it is only those decay products that the detector ever sees. So when two Higgs bosons are produced together, what actually reaches the detector is not two Higgs bosons, but the combined debris of their decays. A specific collection of lighter particles flying outward, the fingerprints of two Higgs bosons that vanished a fraction of an instant after they were born. The entire task of identifying a Higgs pair comes down to recognizing that particular collection of debris and reconstructing, backward from it, the two parent Higgs bosons that must have existed. Let me make this act of reconstruction concrete, because it is one of the most remarkable things human beings have ever learned to do, and it is easy to gloss over how it actually works. The detectors at the Large Hadron Collider are built in layers, wrapped around the point where the protons collide like the rings of an onion. When a particle flies outward from a collision, it passes through these layers in sequence, and each layer is designed to record something different about it. The innermost layers track the precise path of any charged particle, curving its trajectory in a powerful magnetic field so that its momentum can be read from how sharply it bends. A high-momentum particle barrels through on a nearly straight path, while a low-momentum one curls more tightly. Further out, dense layers absorb particles entirely, soaking up their energy and measuring exactly how much each one carried. By the time a particle has crossed all the layers, the detector has assembled a detailed record. Which direction it went, how fast it was moving, how much energy it deposited, and clues about what kind of particle it was. Now consider what happens when a Higgs boson decays. It vanishes, but the particles it turns into fly outward and leave their individual records in the detector layers. None of those records by itself says Higgs boson. Each is just a track and an energy deposit, indistinguishable in isolation from the debris of countless ordinary processes. The reconstruction is an act of inference performed afterward. Physicists take the recorded particles and ask, if I combine these two together, treating them as the decay products of a single parent, what would that parent's mass have been? There is a precise mathematical relationship connecting the energies and directions of decay products to the mass of the thing that produced them. So you can take a pair of recorded particles, combine them, and compute the mass of the hypothetical parent. If you do this for genuine Higgs decay products, the computed mass clusters around the known Higgs mass. If you do it for an unrelated pair of particles that happen to fly out of an ordinary collision, the computed mass scatters all over the place, only occasionally landing near the Higgs value by pure chance. So the genuine signal reveals itself as a concentration of events piling up at the right mass, rising above a spread of accidental combinations that form a smooth background underneath. For a Higgs pair, This inference must be done twice over, and that is where it becomes formidable. You are not reconstructing one vanished parent, but two, from a single spray of debris, and you have to decide which decay products belong to which Higgs boson before you can even compute the masses. Get the assignment wrong, pair up debris from the first Higgs with debris from the second, and you compute nonsense. So the reconstruction involves trying different ways of grouping the particles, testing which grouping yields two parent masses that both land near the Higgs value, and weighing that against the possibility that you are simply being fooled by an ordinary collision that happened to throw out a similar-looking spray. Every step is probabilistic. Each candidate event is not a clean sighting, but a weight of evidence, a judgment that this pattern of tracks and energies more likely came from two Higgs bosons than from the background. The science of Higgs pairs is, at bottom, the science of making that judgment correctly, millions of times over, and trusting the answer only when the genuine events have accumulated into a concentration that mere coincidence cannot explain. The trouble is that the particles a Higgs boson decays into are not exotic. They are the same kinds of particles that ordinary collisions produce in abundance through processes that never involved a Higgs at all. So an ordinary collision can, by chance, throw out a collection of particles that looks remarkably similar to the debris of a Higgs pair. From the detector's point of view, the genuine signal and the imposter can be nearly indistinguishable. You see a certain spray of particles. Was it two Higgs bosons that decayed? Or was it some common process that happens to produce a similar-looking spray far more often? This is the central nightmare of the measurement. The signal is buried not in silence, but in a background that can wear the signal's own clothing. Picking out the real Higgs pairs is not just a matter of finding rare events. It is a matter of distinguishing rare, real events from vastly more numerous fakes that resemble them. This is where the question of how the Higgs bosons decay becomes practically important, and I want to handle this carefully because it would be easy to drown the whole story in a catalogue of technical decay channels, and that is not the point. The essential idea is simpler and more illuminating than any list. A Higgs boson can decay in several different ways, into several different combinations of particles, each with a certain probability. When you produce two Higgs bosons together, each one decays in one of these ways, and the combination of how the two decay determines what the event looks like and how hard it is to find. Some combinations are relatively common, but produce debris that looks almost exactly like ordinary background, making them easy to produce, but agonizingly hard to distinguish from fakes. Other combinations are rarer, but produce a cleaner, more distinctive signature that stands out better from the background, making them harder to produce, but easier to trust when you find one. The experimental strategy involves a trade-off between these. Physicists pursue several decay combinations at once, each offering a different balance of how often it occurs against how cleanly it can be identified, and they combine the information from all of them to build up the strongest possible overall picture. The point is not which specific particles appear in which channel. The point is that there is no single perfect way to catch a Higgs pair. Every avenue forces a compromise between abundance and clarity, and the measurement is strengthened by attacking the problem from multiple angles simultaneously. Consider just one representative example, purely to make the challenge tangible rather than to catalogue. Imagine a case where one of the two Higgs bosons decays into a pair of heavy particles that are themselves relatively common in ordinary collisions. Producing this kind of pair is comparatively likely, which is good. But because those decay products are so common, ordinary background processes flood the same region of data with lookalike events, and digging the genuine Higgs pairs out of that flood is enormously difficult. Now imagine instead a case where one of the Higgs bosons decays into a pair of particles that ordinary processes rarely produce together. This kind of event is rarer, which is bad. But when you do find one, it stands out more sharply against the quieter background, and you can have more confidence that it is real. Neither approach is simply better. One gives you more events, but more confusion. The other gives you fewer events, but more certainty. By pursuing both, and others besides, physicists hedge against the weaknesses of any single approach. This is the practical art of the measurement, and it is why no single decay combination defines the search. Now bring all of these difficulties together, and you begin to see why this measurement demands such staggering quantities of data. Step through the chain of obstacles one more time, because their effects multiply. First, Higgs pair production is intrinsically rare, roughly 1,000 times rarer than single Higgs production, itself a once-in-billions event. Second, the interference between production routes suppresses the rate even further, partially cancelling the very signal we want. Third, the Higgs bosons decay immediately, so we never see them directly, but must reconstruct them from their debris. Fourth, that debris is composed of ordinary-looking particles that mundane background processes produce in overwhelming numbers, so the genuine signal is buried among lookalikes. And fifth, no single event carries the self-coupling on its face. The answer emerges only from the statistical pattern of many events, from the joint reading of total rate and detailed distribution. Each of these obstacles on its own would make for a hard measurement. Stacked together, they make for one of the most demanding measurements human beings have ever attempted. And the only way through is sheer volume. You need so many collisions that even a process this rare and this suppressed yields enough genuine pairs to rise, statistically, above the background of fakes. This is the real reason the Large Hadron Collider runs for years and accumulates collision counts so large they strain comprehension. Quadrillions upon quadrillions of proton crossings. It is not extravagance, it is necessity. To gather even a few dozen, eventually a few hundred, then a few thousand convincing Higgs pair candidates, you must produce and sift through a truly astronomical number of collisions, because the pairs are needles and the haystack is the size of a mountain. To understand why the dataset has to be quite so enormous, it helps to think about how a faint signal actually emerges from a noisy background, because the logic is not as simple as collect more and eventually you will see it. The number of genuine Higgs pairs you collect grows in proportion to how many collisions you run. Double the collisions, and on average, you double the real pairs. That part is intuitive. But the background, the flood of ordinary lookalike events, also grows as you collect more data, and that is where the difficulty sharpens. The genuine signal does not sit on top of a perfectly steady, predictable floor of background. The background fluctuates. In any finite sample of collisions, the number of lookalike events that happen to land in your signal region will randomly vary from what you would expect on average, sometimes a little higher, sometimes a little lower. And those random fluctuations can, by pure chance, pile up in a way that mimics exactly the small excess of events a genuine signal would produce. This is the heart of the problem. When your signal is a faint excess sitting on top of a large, fluctuating background, the question is never simply, do I see extra events? It is, are there enough extra events that random fluctuation in the background cannot plausibly account for them? A handful of excess events means nothing if the background routinely wobbles by that much on its own. To claim a genuine detection, the excess has to be large enough and consistent enough that the odds of the background having faked it become vanishingly small. And here is the crucial point about why volume matters so much. As you accumulate more collisions, the genuine signal grows steadily, but the random fluctuations in the background grow more slowly in relative terms. The noise becomes proportionally smaller compared to the signal as the numbers climb. So, with enough data, a real signal that was indistinguishable from a fluctuation in a small sample gradually lifts itself clear of the noise, rising into a peak that random chance can no longer explain away. The enormous data set is not about collecting the signal alone. It is about collecting enough of it that it can finally be told apart from the background's own restlessness. There is a second reason the data demands are so severe, concerning not the signal, but the background. To recognize a genuine excess, you must know precisely how many look-alike events to expect. If you do not know the background's true size, you cannot tell whether the events you are seeing are in excess at all, or simply the background behaving normally. So an immense effort goes into predicting the background, into calculating, from the known ordinary processes, precisely how many fake events should appear in every region of the data. This prediction must be accurate, because every uncertainty in the background directly clouds the signal sitting on top of it. The larger and better understood your dataset, the more sharply you can pin down the background, and the more confidently a genuine excess can be separated from it. And it is not enough to simply collect the data, you must also understand the background with extraordinary precision. To claim that you have seen genuine Higgs pairs above the lookalikes, you have to know exactly how many lookalikes to expect, so that any genuine excess stands out as real rather than as a statistical accident. This demands not only enormous datasets, but exquisitely careful modelling of every ordinary process that could imitate the signal. A vast theoretical and computational effort running alongside the experimental one. The measurement is therefore a marriage of brute force and delicate precision, overwhelming quantities of data on one side, and meticulous understanding of the background and the interfering signal routes on the other. I want to be honest about where this leaves us, because the temptation to declare victory prematurely is strong, and it must be resisted. Despite all this effort, the measurement of the Higgs self-coupling is not yet a finished, precise result. Physicists have searched for Higgs pair production with everything the current collider can offer, and they have begun to set meaningful limits, bounding how strong or weak the self-coupling could possibly be, ruling out the more extreme possibilities, narrowing the range within which the true value must lie. They have, in the most favourable decay combinations, started to glimpse the faintest possible evidence that the process is occurring. But a clean, confident, precise measurement of the self-coupling, one that pins down the curvature of the potential with real certainty, and either firmly confirms the standard model's prediction or firmly contradicts it, remains beyond the reach of the data gathered so far. We are at the threshold, constraining and bounding and glimpsing, but not yet declaring. The interference is too subtle, the signal too rare, the background too treacherous, and the data, vast as it already is, not yet vast enough. This is a measurement that the current era of the collider has begun, but that future runs, with far larger datasets, are designed to bring to fruition. And this honest accounting actually deepens the appreciation of what is at stake. The reason physicists are willing to pour years and enormous resources into a measurement that may not be fully resolved for a long time is that the prize is so fundamental. Buried inside that suppressed, interfering, debris-obscured pair production rate is a number that tells us whether the field filling all of space obeys the self-interacting rule the theory assigns it. The difficulty of extracting it is not a sign that the question is unimportant. It is a sign of how deeply the answer is hidden, how well protected the self-interaction is behind the rarity and the interference and the background. We are not struggling because the goal is trivial. We are struggling because the goal is profound, and nature has buried it about as deeply as anything can be buried. So let me consolidate the picture we have built, because it is now complete in its essential structure. Two Higgs bosons can be made from a single collision through more than one quantum root. One route runs through a single virtual Higgs that splits in two via the self-interaction, and therefore carries the self-coupling within it. Another route makes the pair without ever invoking the self-coupling. These routes interfere, and they interfere destructively, partially cancelling and further suppressing an already rare process. Because of this interference, the relationship between the self-coupling and the observed rate is not simple, and the same rate can be consistent with more than one value of the self-coupling. No single event reveals the answer. The self-coupling emerges only from the combined rate and the detailed distributions of many events. Those events must be reconstructed from the decay debris of the vanished Higgs bosons, debris that ordinary background processes can imitate in overwhelming numbers. Disentangling the genuine signal from the lookalikes across multiple decay combinations, each with its own balance of abundance and clarity, demands enormous datasets and meticulous modelling. And even with all of that, the measurement is, for now, a matter of bounding and glimpsing rather than precisely pinning down. That is the gauntlet. It is the gap between the elegant principle, Higgs pairs are sensitive to the self-interaction, and the punishing practice of actually measuring it. But the practice, for all its difficulty, is pointed at something worth every ounce of the effort. Because once we can measure the self-coupling, even roughly, we gain the power to ask a question that reaches far beyond the catalogue of particles. We gain the power to ask whether the shape of the potential matches the standard model, and if it does not, what that might mean. And the answer, whatever it turns out to be, does not stay confined to a tunnel beneath the Alps. It reaches outward, to the first instance of the universe, to the question of how the field came to rest where it did, and even to the long-term fate of the vacuum we all live inside. That is where this story turns next, from the difficulty of the measurement to the magnitude of what the measurement could reveal about the deepest structure and history of reality itself. So let us ask the question that justifies the entire heroic effort. Suppose physicists succeed. Suppose that, after years of running and datasets of almost incomprehensible size, they finally measure the rate of Higgs pair production with real precision and extract from it a value for the self-coupling. A number describing how strongly the field that fills all of space interacts with itself. What would that number actually tell us? What hangs on whether it matches the standard model's prediction or departs from it? The answer is that this single measurement reaches far beyond the tidy business of confirming a theory. It touches the question of why the universe took the form it did, how it behaved in its first instance, and even whether the ground we all stand on, the vacuum state of the field, is truly stable or only temporarily so. The self-coupling is not just another entry in a table of particle properties. It is a probe of the deepest layer of the structure of reality, and the consequences of measuring it ripple outward in every direction. Begin with the simplest possibility. The measurement matches the prediction. The standard model, as we have discussed, does not leave the self-coupling free to be anything at all. Given the Higgs mass and the resting value of the field, both of which we have already measured, the theory fixes what the self-coupling ought to be. It hands us a specific number derived from its own internal logic. If physicists measure the self-coupling and find that it agrees with this prediction, that would be a triumph of a particular and profound kind. It would mean that the shape of the Higgs potential, the very curvature of the landscape that the universe rests in, is exactly what the theory says it is, not just near the bottom of the trough where the field sits, which we already knew from the Higgs mass, but in the broader region away from the resting point, which we have never before been able to test. It would confirm that the field obeys the self-interacting rule the standard model assigns it, all the way down to its self-referential core. It would close one of the last great open verifications of the theory, demonstrating that our description of the foundation of reality holds together even in the one corner that has so far evaded all measurement. That kind of confirmation might sound, at first, like an anticlimax. The theory was right, as it has so often been right. But do not underestimate what it would mean. The Standard Model is the most precisely tested theory in the history of science, and yet we know it cannot be the complete story. It says nothing about the gravity that shapes the cosmos. It offers no explanation for the dark matter that outweighs ordinary matter many times over. It cannot account for why the universe is filled with matter and almost no antimatter. So every place where the Standard Model has not yet been tested is a place where the cracks might first appear, a place where the new physics we know must exist somewhere might finally announce itself. The self-coupling is exactly such an untested place. To measure it and find agreement would be to confirm that even in this deeply hidden corner, the field behaves as predicted, and that whatever lies beyond the Standard Model does not announce itself here, at least not at the precision we can currently reach. It would be a powerful statement about where new physics is not, which is itself a way of narrowing the search for where it is. Now consider the far more dramatic possibility. The measurement does not match the prediction. Suppose physicists measure the self-coupling and find that the field interacts with itself more strongly, or more weakly, or in some altered way compared to what the Standard Model demands. Suppose the rate of Higgs pair production, once the interference and the background are accounted for, simply does not line up with the theoretical expectation. This would be one of the most significant discoveries imaginable, because it would mean that the shape of the Higgs potential is not what we thought. The curvature of the landscape away from the resting point would be revealed as different from the Standard Model's prediction, and that difference would be a signpost pointing toward physics we do not yet understand. A deviation in the self-coupling would not merely be an anomaly to be filed away. It would be evidence that something beyond the Standard Model is reaching in and reshaping the most fundamental field in nature. What could cause such a deviation? Broadly, there are two kinds of explanations, and both are profound. The first is that the self-interaction itself is genuinely altered, that the potential has a different shape than the simple prediction, perhaps because the true theory of the Higgs field is richer than the Standard Model's minimal version. The second is that there exist new particles or new fields, not yet discovered, that participate in the production of Higgs pairs, and thereby distort the rate or the distribution of events away from what the known processes alone would produce. These additional players could subtly insert themselves into the quantum routes we discussed, interfering in new ways, opening new pathways, leaving their mark on the pattern of pairs, even if we never produce those new particles directly. In either case, a deviation in the Higgs pair measurement would be a window onto a layer of reality beyond our current theories, either a different potential than we imagined, or new ingredients in the universe that betray their presence through their effect on how the Higgs field raises two ripples at once. I have to be very careful here, and I want to be explicit about it, because this is exactly the kind of place where excitement runs ahead of evidence. None of this new physics has been discovered. We have not measured a deviation in the self-coupling. We have not found new particles lurking in the Higgs pair data. Everything I have just described is a possibility, a reason the measurement matters, a set of doors it could potentially open, not an announcement that any of those doors has been opened. The honest situation, as we established, is that physicists are still bounding and constraining the self-coupling, ruling out the more extreme values, glimpsing the faintest hints of the process, but not yet measuring it precisely enough to say with confidence whether it matches the prediction or departs from it. The power of the measurement lies in what it could reveal, and that potential is reason enough to pursue it relentlessly. But we must not dress up potential as fact. The Higgs pair program is exciting precisely because the answer is not yet known, and because either answer, confirmation or deviation, would teach us something we deeply want to learn. What we cannot do is presume the deviation before the data deliver it. With that caution firmly in place, let us follow the deeper consequences of the self-coupling outward, because this is where the measurement stops being a matter of particle bookkeeping and becomes a question about the universe itself. The shape of the Higgs potential is not merely a detail of how one field behaves. It is tied to one of the most important events in the history of the cosmos, the event physicists call electroweak symmetry breaking. To understand why this matters, we have to go back to the earliest moments of the universe, when everything was unimaginably hot. In the first tiny fraction of a second after the universe began, conditions were so extreme, the temperature so staggeringly high, that the Higgs field did not rest in the trough where it sits today. At those temperatures, the energy of the surrounding environment was so great that the field was, in effect, shaken out of the trough entirely. The landscape that determines the field's behavior depends on the temperature, and at sufficiently high temperatures, the shape changes. The trough that holds the field at a non-zero value today flattens out, and the field's comfortable resting place becomes the center at zero. So in the earliest, hottest instance, the Higgs field sat at zero, and the universe was in a fundamentally different state than the one we inhabit now. The distinction between certain forces that we treat as separate today was, in that hot early phase, erased. The universe possessed a symmetry that it does not possess now. Then, as the universe expanded and cooled, the temperature dropped. The shape of the potential shifted toward the trough we know today, and at a certain moment, the field rolled off the central hill and settled down into its non-zero resting value. This rolling down, this transition of the field from sitting at zero to sitting in the trough, is electroweak symmetry breaking. It is the moment the Higgs field switched on, so to speak, the moment it took up the permanent non-zero value that pervades all of space today, and gave the universe the structure we now observe. And the way this transition unfolded, how smoothly or how abruptly the field rolled into its trough, depends sensitively on the shape of the potential. The very same shape, the very same curvature that the self-coupling measures. So when we measure the self-coupling, we are not only testing the field's behavior today, we are gathering evidence about the form of the potential that governed one of the most consequential transitions in cosmic history. This connection is genuinely remarkable, so let me draw it out. The nature of the electroweak transition matters for some of the deepest unsolved questions in physics. One of the great mysteries of the universe is why it is filled with matter and contains almost no antimatter. When we look at the laws of physics in their most basic form, matter and antimatter appear nearly symmetric, and yet the cosmos is overwhelmingly made of matter. Something in the early universe must have tipped the balance, generating a slight excess of matter over antimatter that survived to form everything we see. One of the leading ideas for how this might have happened depends critically on the character of the electroweak transition, on whether the field rolled into its trough gradually and smoothly, or whether it did so in a more violent, abrupt fashion, more like water suddenly freezing than like a gentle settling. A more abrupt transition could, under the right conditions, have helped create the imbalance between matter and antimatter. And whether the transition was gradual or abrupt depends on the shape of the Higgs potential, which, once again, is what the self-coupling probes. So a measurement of the self-coupling that revealed an unexpected shape to the potential could bear directly on the question of why the universe is made of matter at all. I want to be measured here, because this is another place where it is easy to overreach. Measuring the self-coupling will not, by itself, hand us a complete reconstruction of the early universe or resolve the matter-antimatter mystery in one stroke. The connection is real, but indirect. The self-coupling is one crucial piece of information about the shape of the potential, and the shape of the potential is one crucial input into the story of the electroweak transition, which is in turn one possible part of the story of why matter prevailed. Each link in that chain is genuine, but no single measurement collapses the whole chain into a finished answer. What the self-coupling offers is a constraint, a clue, a piece of a puzzle that connects the behavior of a field measured in a collider today to events that shaped the cosmos in its first instance. That connection alone, that a number extracted from rare collisions beneath the Alps speaks to the conditions of the newborn universe, is extraordinary, and we do not need to inflate it into a claim that Higgs pairs alone can rewind cosmic history. The truthful version is wondrous enough. There is yet another, almost vertiginous consequence of the shape of the potential, and it concerns not the past, but the future, the long-term stability of the universe itself. Remember that the Higgs field rests in the trough of its potential, at the lowest point it can find, and that this resting place is the vacuum state, the ground the universe sits on. We naturally assume that this resting place is permanent, that the field will stay where it is forever, that the vacuum we inhabit is the true and final lowest point. But whether that assumption is correct depends, once again, on the full shape of the potential, on what the landscape looks like not just near the trough where the field rests, but far away from it, in regions we have never been able to probe. And here the self-coupling, which carries information about the curvature of the potential away from the resting point, becomes relevant in the most dramatic way imaginable. It is conceivable, depending on the true shape of the potential, that the trough the field currently rests in is not the absolute lowest point of the landscape. It might be only a local low point, a comfortable hollow that the field has settled into, but with an even lower valley somewhere farther out, separated from us by a hill. If that were the case, then the vacuum we live in would not be the true ground state of the universe, but a metastable one, stable for an enormously long time, but not truly permanent. In such a scenario, the field could, in principle, after a span of time so vast it dwarfs the current age of the universe many times over, find its way over or through the hill and roll down into the deeper valley, transforming the vacuum into a different state with different properties. This is the question of vacuum stability, and it is one of the most sublime and unsettling questions in all of physics. Is the ground we stand on truly the bottom, or merely a ledge above a deeper drop? The shape of the Higgs potential determines the answer, and the self-coupling is part of how we read that shape. Current estimates, based on the values we have measured so far, suggest that our vacuum sits in a delicately poised situation, possibly stable, possibly metastable, but with a lifetime so long that there is no cause for any practical concern, vastly longer than the universe has existed or will exist in any form we would recognize. What determines which side of that knife edge we fall on is a quiet tug-of-war between two of the quantities we have already measured, and understanding it reveals just how finely balanced our universe appears to be. The shape of the Higgs potential, far from the resting point, the very region that decides whether a deeper valley lurks beyond the hill, is not fixed once and for all by the values we measure today. It is pulled in opposite directions by different particles, through the way they continuously interact with the Higgs field in the restless quantum vacuum. The heaviest known particle, the top quark, exerts a pull that, at field strengths far beyond the resting point, tends to drag the potential lower than it would otherwise sit, threatening to open a deeper valley out there and to leave our vacuum merely a ledge above it. The Higgs-boson's own mass, meanwhile, exerts a pull in the opposite direction, working to keep the potential rising and our resting place the true bottom. Whether the landscape ultimately turns downward into a deeper valley or holds firm depends on the precise contest between these competing influences. And here is the striking part. When you plug in the masses we have actually measured, the heavy top quark on one side, the Higgs boson on the other, the contest comes out almost exactly even. We do not land safely in the region where the vacuum is unmistakably the true bottom, nor clearly in the region where it is plainly a ledge. We land right at the boundary between them, balanced on the edge, where small shifts in the measured quantities could tip the conclusion one way or the other. Why the universe should sit so precisely at this threshold is itself a mystery no one fully understands. It may be coincidence or a clue to something deeper. Either way, it places enormous weight on measuring the relevant quantities precisely, and the self-coupling, which carries direct information about the curvature of the potential away from its resting point, is one of the inputs that could sharpen this verdict. A precise measurement of how the field interacts with itself would help tell us, with greater confidence than the indirect pulls alone allow, whether the ground beneath all of existence is truly final, or only a long resting place above a deeper one. But the precision of this conclusion is limited by how well we know the relevant quantities, and the self-coupling is one of the inputs that could sharpen or shift the picture. A precise measurement of the self-coupling, by constraining the shape of the potential, would help us understand more clearly whether the vacuum is truly stable or merely long-lived. I emphasize again, lest this be misunderstood. There is no looming catastrophe, no practical danger, nothing here that should disturb anyone's sleep.
The relevant timescales are so immense as to be meaningless on any human or even cosmic scale we ordinarily contemplate. The point is not alarm. The point is that the very same number we are struggling to extract from rare collisions speaks to a question of the most profound generality. Whether the universe we inhabit rests on a foundation that is truly final, or one that is, in the deepest sense, provisional. Step back and take in the full sweep of what the self-coupling touches. It tells us whether the Standard Model's account of the field's self-interaction is correct, closing or cracking one of the last untested verifications of our best theory. It bears on the nature of electroweak symmetry breaking, the transition by which the Higgs field switched on and gave the universe its structure. It connects, through that transition, to the question of why the cosmos is made of matter rather than nothing. And it informs the question of whether the vacuum we live in is truly stable. From a single, fiendishly difficult measurement of how often a field raises two ripples at once, threads run outward to the origin, the composition, and the ultimate fate of the universe. This is why the self-coupling matters for so much more than the classification of particles. A particle classification tells you what exists. The self-coupling tells you about the behavior of the thing that underlies existence, the shape of the field that fills all of space, the landscape the universe settled into, the foundation everything else is built upon. And this is precisely why producing two Higgs bosons at once is worth the staggering effort it demands. Everything we traced earlier conspires to bury this measurement about as deeply as nature can bury anything. The scarcity of the process, the way its production routes cancel against one another, the vanishing of the bosons before any instrument can see them, the ordinary collisions crowding in to disguise the few real events. But difficulty, in science, is not the same as importance. The more deeply a thing is buried, the more it suggests nature had reason to hide it. And the self-interaction is buried precisely because it sits at the foundation, untouched by every easier measurement we know how to make. So physicists press on, not in spite of the difficulty, but because of what it implies. That the answer on the far side is fundamental enough to have been protected this well. The effort is proportional not to the ease of the measurement, but to the magnitude of what it could reveal. So let us return, finally, to where we began, and to the question in the title that has guided us all along. Why is CERN trying to make two Higgs bosons at once? Now we can answer it not as a slogan, but as the culmination of everything we have built. In 2012, the discovery of a single Higgs boson answered a question that had stood for half a century. Does the Higgs field, the invisible presence predicted to fill all of space, actually exist? The answer was yes. A single ripple in the field, caught in the detectors beneath the Alps, confirmed that the field is real, that it pervades the universe, that the foundation the theory had described was truly there. But that discovery, monumental as it was, answered only the question of existence. It told us that the field is. It did not tell us how the field behaves toward itself. That deeper question, how the Higgs field interacts with itself, what the shape of its potential truly is, whether it obeys the self-interacting rule the Standard Model assigns it, cannot be answered by a single Higgs boson. A single ripple never involves the field touching its own presence, and so it carries no information about the self-interaction. The only known way to make the field reveal how it acts upon itself is to force it to raise two ripples together from a single collision, to produce a genuine Higgs pair born from one event, the rarest of the rare.
Because only when the field raises two ripples at once does the self-interaction enter the picture. Only then does the curvature of the potential away from its resting point leave its mark. Only then does the field tell us not merely that it exists, but how it is shaped. That is the whole reason for the endeavour. One Higgs boson proved the field is there. Two Higgs bosons, born together in a single violent instant, may finally reveal how that field acts upon itself. And so the image we have carried throughout comes into its full meaning. Somewhere beneath the border of France and Switzerland, in a ring colder than the depths of space, protons are crashing together at nearly the speed of light, hundreds of millions of times each second, and once in a vast while, the field that underlies all of reality shudders hard enough to raise not one ripple, but two. Both vanish almost instantly, leaving only a faint and scattered trace in the debris. Physicists gather those traces, painstakingly, across years and across datasets of staggering size, sifting the genuine pairs from a roaring background of imposters, disentangling the quantum roots that interfere within them, comparing the rate and the pattern of what they find against what the theory predicts. They do this not to add another particle to a catalogue, but to read the shape of the landscape the universe rests in, to test whether the foundation of reality behaves the way our best theory claims, and to glimpse, through that test, the conditions of the newborn cosmos, the reason matter prevailed, and the question of whether the ground we stand on is truly the bottom or only a ledge. This is the journey that the discovery of a single Higgs boson began rather than finished. We have moved, in the span of this story, from proving that the Higgs field exists to confronting the far harder task of understanding how that field behaves. The first was a question of presence. The second is a question of character. And the bridge between them, the only bridge we know how to build, is the production of two Higgs bosons at once. Each rare pair is a whisper from the deepest layer of nature, telling us not whether the foundation is there, we know that now, but how that foundation is shaped, how it responds to itself, how it came to rest where it did, and what that might mean for everything built upon it. That is why physicists chase the rarest of ripples beneath the mountains. Not to confirm that the field exists, but to finally understand what the field truly is.